Okay, so let's summarize this topic. So the problem that we try to address is how do we choose the action? Stateless MDP, we have the same set of actions available at each time step, and the same decision is the correct decision at each time step, right? The action space and the reward distribution doesn't change between time steps. So we would like to choose the action that results in the highest expected reward. Actually, we would like to converge to learn that action over time and converge on it. We had several assumptions. Number one, that the action's expected reward is unknown. If we know it, of course, we don't need to learn anything or converge. Assumption number two is that we are confronted with the same problem over and over again. So this is the stateless MDP problem, or the multi-arm bandit problem. Number three, we are able to observe an action's outcome once chosen. It's very important in order to allow us to do reinforcement learning, right? We saw several approaches. So we saw an approach that learns the action's expected reward through exploration. So this is a value-based approach, a Q-learning. Or we saw a different approach to learn a policy directly. So a policy-based approach, we just saw that. And then we would like to exploit the learned knowledge to choose the best action or to converge on it over time. We saw several variants of these methods. We saw a greedy approach. We saw that it has an issue with exploration. It doesn't perform sufficient exploration, but we saw that this can be mitigated by initializing the initial estimate by optimistically. An optimistic initialization approach. However, we also said that this might be an issue in highly stochastic environments. But we saw that it results in pretty good results if you set the learning rate correctly and if your environment is not highly stochastic. Then we discussed a simple epsilon greedy approach. Then we moved on to discuss more advanced exploration techniques, such as the UCB approach, the upper confidence bound approach, and finally the softmax activation function, which results in a Boltzmann distribution as the exploration approach, right? We saw that specifically when we pair that with gradient-based methods, because the softmax activation is differentiable, which is helpful or allows policy gradient approaches. Which one of these works best? Well, the answer is mixed. I can show you the results for our example problem, the benchmark problem that we saw over and over throughout this topic, but the answer might vary in different domains, right? So it's highly domain dependent. But for the specific problem that we've seen during this topic, you can see that. So on the y-axis is just the average reward over first 1,000 steps. So this is not the training curve that we've seen previously. How do we train over time? But this is after 1,000 steps, the result after 1,000 steps. Once not necessarily converged, but the initial learning has been performed. And these are the results for each one of the approaches that we learned: epsilon greedy, UCB, gradient-based approach, and greedy with optimistic initialization. And for each one of these approaches, we saw several hyperparameters, right? Epsilon, alpha, C for UCB, and Q0. So each one of these hyperparameters will impact the performance, and you can see that these algorithms perform better for different hyperparameter values, but you can see here, specifically for this problem, that UCB resulted in the best performance. After that, we had the epsilon greedy, then gradient-based, and finally an epsilon greedy approach. But these are not general trends. UCB specifically is actually quite limited with its ability to generalize, because it requires us to count the number of times that we sampled each action in each state. UCB has some issues with generalizing to MDPs. We'll discuss this later on. Optimistic initialization, as I said before, it can be problematic in highly stochastic environments and non-stationary environments. It's, in different domains it can break down very quickly. And gradient-based approaches, and actually also epsilon greedy, so in DQN, epsilon greedy approaches, as well as gradient-based approaches, they actually, in many domains, they are, I would say, the state of the art. Or some combination of these two, an actor-critic combination of these. So these results are interesting just to get a sense of what happens in the benchmark problem that we discussed, but these are not general, okay? And these might change significantly in different domains. Okay, next we're gonna start discussing Markov decision processes, defining the more general MDP case. Regarding assignments, please you should start working on the, with respect to assignments, first of all, the quiz, it's not by September 3, so the first quiz is already up on Canvas. Please be sure to complete this by the deadline that I'll publish on the Canvas website. It changes between semesters, so please check the deadline on Canvas. But please take the quiz. Usually you have about a week to finish this quiz after the relevant lecture is uploaded. Then please go over the tutorials, the linear algebra, basic probability, Python, NumPy, Gym, the Gym environment or gymnasium environment. Hopefully you already started these. If not, please do and try to complete those. Also, going over these tutorials will help you understand if you're in a good shape towards completion of this course, right? And for your project, please go over the project description and the timeline, and please find a partner. And we have a relevant discussion board for finding partners on CampusWire. That's it.